All right, welcome to Chapter 3. Let me finish getting it blown up here. And this says 3A, that is a typo. You're not looking for a second PowerPoint, it is just this one. So in this PowerPoint, we are going to talk about cell metabolism. In this first half, I should say. We'll continue to talk about cell metabolism in the second half, but we're just going to start here. So, when we are talking about cell metabolism, we need to talk about what it is. So metabolism is the sum of all chemical reactions occurring in a cell. So when I say metabolism, you probably think of the societal expectation of metabolism is how much energy you burn. That's only half true. It is half of the equation. Metabolism is both what you burn and what you make. However you want to look at that. It's what you break down and what you build. And essentially all energy metabolism is going to actually mean is energy being stored and energy being used. So making energy particles, whether it's for short or long-term storage, ATP versus a triglyceride, or actually using that energy. These reactions come in a variety of different formats, but they all have a base reading, so to speak. We're going to have reactants or substrates, when we talk about it from a biological standpoint, that will have some sort of reaction. I don't want to use that term because we're talking about reactions, but they'll have some sort of effect on each other that will end up making a product. So you'll see stuff like A plus B becomes C plus D. The arrow indicates the direction that the change is occurring in. So a arrow pointing towards the right means reactants are transformed into products. If the arrow is pointing towards the left, it means products are transformed into reactants. But most of the time, the way the reactions are usually shown is this double arrow. It's pointing in both directions because most reactions are bidirectional. It's not occurring in one direction only. You usually have at least a little bit occurring in the opposite. And you can actually show that by having a big arrow pointed towards this is what's primarily happening, and then a little arrow going the opposite direction. So, metabolic reactions. These are chemical reactions that occur in the body, and these are defined as either being catabolic or anabolic. If it is a catabolic reaction, it is going to break large molecules into smaller ones. So, catabolic, think digestion, so to speak. That would be an example of it. If we are talking about anabolic reactions, this is going to be the synthesis of larger molecules from smaller ones. So this is going to be making. So think about making protein chains. Anabolic is making protein chains. Now we can chain these reactions together, and this is called a metabolic pathway. This is actually very, very common in biology. When we talk about cellular respiration, the creation of ATP, it is a metabolic pathway. A becomes B, which becomes C, which becomes D, which becomes E, which becomes F, and so on down the line until we get to the very end. So we're going to start off with an initial substrate, and then everything in between the beginning and the end is known as an intermediate, and then we have the final end product. When we talk about metabolic reactions, we're going to talk about them in a couple of categories. They're either going to be a hydrolysis condensation reaction, a phosphorylation dephosphorylation reaction, which is a variation on hydrolysis, or a oxidation reduction. So let's start with hydrolysis. A hydrolysis condensation reaction is going to be AB plus a water molecule is going to become an AOH plus HB. So basically, we have our substrate here, which is a combination of A and B, plus this water molecule. One half of the substrate is going to go with the OH of the water, and the other half of the substrate is going to go with the remaining hydrogen. An example of this one would be if I take a sucrose molecule and I insert a water molecule into the bond, I end up with the monomers glucose and fructose. Condensation is simply the opposite. I take my two molecules, I remove a water molecule from them, and I wind up with a product that is a combination of those two substrates plus a water molecule. So just reverse what we just did. I take my glucose and my fructose, I remove a water molecule from them, bonding them together, giving me a sucrose plus a water. So condensation is, you're going to end up with water as a byproduct. Hydrolysis, you're going to use water to break a bond. Phosphorylation and dephosphorylation is a riff on that, a spin on that, a variation, whatever term you want to use. We're still either adding or removing a water group, but we're also adding or removing a phosphate group. So for instance, if I have a substrate and a phosphate, and I remove a water, I'm going to get a water as a byproduct and the substrate plus phosphate. So example given, I have ADP plus a phosphate group, and they bond together. And how do they bond together? I remove a water molecule from the ADP and from the phosphate, so I get ATP plus water at the end of my reaction. Dephosphorylation is simply the reverse of that. Except, we're still going to, not an except, hold on. Phosphorylation is, I'm right. I confused myself, sorry. Phosphorylation is a condensation reaction because we're removing a water. Yeah. And dephosphorylation, so the removal of a phosphate group, is a hydrolysis reaction. I insert a water into the bond, breaking off a phosphate, and I end up with a ADP and a phosphate group. So phosphorylation is a condensation, dephosphorylation is a hydrolysis. Yeah. Oxidation and reduction have to do with the adding and removal of electrons. So oxidation is going to be I remove an electron. So if I have this AB, A plus B, I get A losing an electron, it becomes oxidized, and B is gaining an electron, so it becomes reduced. Real-world examples are great to try and wrap your head around this. If I have this hydrogen molecule, it's two hydrogens bonded together, and I lose two electrons, so I have two free-floating electrons, in theory, I get two H pluses and two free-floating electrons. Better example, if I have a glucose and six oxygen molecules, I will wind up with 6 CO2s and 6 H2Os. And it has to do with where those electrons are being added and removed from. Truthfully, the classic example we're going to see in biology is the removal and addition of a hydrogen ion. Hydrogen ion. So if I have this molecule, and there are hydrogens on each end, I can chop off those two hydrogens and get this product, AB, plus 2 hydrogen ions. That's the most common example of this oxidation that we see. Reduction is when we take an electron and we add it to something. So I have my 2 hydrogen ions and I have my 2 free-floating electrons. If they go back onto an atom, we would get that. Or algebraically, it'd look like this down here. So reduction is the addition of ions, oxidation is the removal. All right. What is energy? Why do we care about it? Energy is the capacity to do work. It comes in 2 varieties, kinetic and potential. Kinetic energy is going to be associated with motion. So kinetic energy, think doing. So things like thermal energy, radiant energy, electromagnetic, electrical, those are all associated with doing. It's associated with motion. Potential energy is stored energy. So this is going to be your chemicals, your mechanicals, your nuclear, your gravitational. They all have the potential to do something. Which means, if we're talking about energy, we have to get into the first and second laws of thermodynamics. With the first law being, energy in the universe is considered a closed system, is constant. You can neither create it nor destroy it. It is neither added nor removed. That is a closed system. The human body, on the other hand, is not a closed system. The human body is what we call an open system. I can add energy into the system and I can remove it. How do I add energy? I eat. How do I remove energy? I do things. It's as simple as that. The universe is closed. I can neither add nor remove. The human body is wide open, and I can add energy and remove it from it. The second law of thermodynamics is basically saying processes proceed in the direction that spreads out energy. Energy wants to get smaller. It is the natural inclination for big molecules to break down into smaller molecules. Molecules specifically, want to move from high to low concentrations. They want to spread out. They want to even everything out. This concept, by the way, of movement of molecules from high to low concentration is known as diffusion, and we will be talking more about that in Chapter 4. I think it's in Chapter 4 anyway. It's 3 or 4. It's somewhere in this first module. All right, so here's the thing. Most of the time in a biological unit, reactions are not standalone. You don't have things happening in one direction. They're what we call coupled. I'm going to have a reaction going towards the right, but I'm also going to have a reaction going towards the left. Why is that? All reactions are going to need to involve an exchange of energy because molecules possess energy. So really these equations should be reactant plus energy equals product or reactants equal products plus energy. Reactions are either going to consume energy or give off energy. And that change in energy, whether they're consuming or using it, is denoted by a change in E. So this little triangle, anytime you see this little triangle, this is going to denote change in, and then this capital E denotes energy. So change in energy is energy of the products minus the energy of the reactants. So for instance, if I have my reactants and they release energy to get to my products, they give off energy, that is going to have a negative change in E. So negative 300, negative 400, whatever the case may be. Which brings us to exergonic reactions. Reactions that give off energy. Energy is a byproduct of the reaction are known as exergonic. typically these are going to be your catabolic reactions, so your breakdowns. We have a change in potential energy. These tend to be spontaneous, so they're going to happen with no input or very little input. And the energy of the reactants is greater than the energy in the product. So energy is a byproduct, as I mentioned. What tends to happen is these energy-releasing reactions, these exergonic reactions, tend to be coupled to an energy-requiring reaction. So the energy given off fuels the reaction that needs energy. It gives it off, and it's immediately consumed by the reaction that needs to use it. A reaction that needs energy to be added into it in order for it to happen is going to have a positive change in E. So this is going to be a plus 300, a plus 400, something like that. And they're known as endergonic reactions. Endergonic reactions are going to be our anabolic reactions. These are going to be the building reactions. Again, we're going to have a change in potential energy, but it is not going to be spontaneous. The energy in our reactants is going to be less than the energy in our products, and so we're going to need to put in energy in order to make it happen. A unit of energy is going to be expressed in calories or joules. 1 calorie is going to equal 4.18 joules. And what is a calorie? A calorie is the amount of energy that is required to raise 1 milliliter of water by 1 degree Celsius. So how much energy do I need to sink into this water to raise its temperature by 1 degree Celsius? That's a calorie. It's one of the things that makes water such a fantastic solvent, and it's one of its unique properties is the fact that it can absorb a ton of energy before its temperature changes. Now, chemical equilibrium, this is the ideal. When the rate of forward and reverse reactions are equal, so there's no net change in concentration of products or reactants, the change in energy is 0. This is chemical equilibrium. Everything is perfectly balanced on both sides. How likely is this to happen? Slim to none. Naturally speaking, anyway, at least. While this is what it's striving for, it is hard to meet. And I cannot think of an example of when the body actually does it. All right, you might be looking at this equation and going, oh my goodness, I have to memorize this. No, you don't. Nope. Calm your panic. Okay, there's this thing called law of mass action. Basically, if I increase the amount of reactants, it is going to push the reaction to occur. So if I increase the amount on the left side of the equation, it's going to push the equation towards the right. If I increase the product concentration, it's going to push the reaction in the reverse. So if I increase the amount on the right side of the equation, it's going to push the breakdown of the products back into the reactants. Basically, that equilibrium, wanting to become balanced on both sides. The more I add on the left, the more it's going to push right to try and balance it. The more I add on the right, the more it's going to push left to balance it. And that's basically what this is saying. The little a is on the left side, the big A is on the right. So A plus B is going to be the equivalent of C plus D. Actually, the little letters are the number of molecules, but it's still the same thing. Which means we get that lovely equation at the bottom, which is the equilibrium constant, which is K. Will you ever need to calculate the equilibrium constant? Not in this class. Maybe in chemistry or organic chem, but not in physiology. We typically will give you the constant. We've already worked it out. And for those of you who like images to help with visualizing what that was talking about, this is a visualization of that constant, of that concept. And this is showing you what happens when you add in more of that reactant and how it adjusts accordingly. All right, now we need to talk about something called activation energy. Sorry. What is activation energy? Okay, so we mentioned that some reactions occur spontaneously. They give off energy. And some reactions need energy. Regardless of whether or not the reaction gives off or needs energy to happen, they all need a little bit of energy to get going. So there's this thing called a transition state, which is where we have the reactants and they're, for lack of a better term, thinking about becoming the products. They're kind of milling around. The bonds are shifting a little bit. And when a certain amount of energy is put in to the reactants, we are going to get the reaction to actually occur. The amount of energy is known as the energy of barrier or activation energy barrier. We just shortened that down to activation energy. It is the amount of energy that needs to be put into the equation to make the equation happen. And because energy needs to be put in, it is going to limit how fast the reaction occurs. And it is demonstrated with this graph. So we have our reactants, we put in energy, and then we're going to come down to our products. This is actually an example of a reaction that gives off energy, but it would be the same concept even if we needed to put in even more energy to make it to happen. So just another example of that. Again. And again. All right, at this point, you're going to pick up with the second audio.